In the previous video, we have already discussed about linear regression theory and the math behind it. Now let's see some practical example with the help of some data set. Okay, so in this video, we'll be observing or we'll be going through some data set that is salary data set. Okay, so in this salary data set, we have years of experience. Okay, and the output field that is salary. So, what do you guys think? So, with the increase in years of experience, will the salary increase or decrease? In general, it will increase, right? Let's say for 1 year guy, if the normal industry level salary is, let's say, some 13 lakhs. Okay. And if it's increasing, like the years of experience is increasing 2 years, 3 years, like that, if it is keep on increasing, in the same manner, the salary will also increase, right? So this we can think of it as some linear function between years of experience and salary, and this we can definitely like we can think of some linear regression kind of algorithm. So in linear regression, we have already seen previously, like we'll be having some data points. In this, our input is years of experience, whereas our output is salary. In either thousands or lakhs, the scale can be anything. So our output column is salary, whereas our input column is years of experience. And we'll be having a data set in that there will be so many data points like this. Okay. So these will be collected from real world data. So the data might not be in like continuously in straight line. It might be looking like this if we plot. So for such kind of thing, we have already discussed it is better to apply linear regression, and we have discussed the math also. Now let's see practically how we'll be coding it with the help of Python. So for this, we'll be using some library called as sklearn. So in this sklearn, all the things that we have discussed in the previous class, like a hypothesis, loss function, and also what is the last step, optimizer, all these things like are already implemented. We just need to like use that library and load those functions. That's it. So it will be really simple. Let's see how to do that. Okay. So I'll be showing you. So in this, first we'll be importing all the required libraries. First, I'm importing NumPy, Matplotlib, Pandas, all these things. And in general, all these data sets will be in the form of CSV files. So like in salary datasets.csv, we are having this particular CSV file, and it can have multiple columns. Okay, so let's try to open that and see. So this is our salary dataset, and if I open it, let's observe. Here we are having one column that is some index column simply, and then we are having years of experience and salary, corresponding salary. So this is the data that we are having, but we don't need this, right? So either we want years of experience and this salary. These two columns are only like we are interested in. So we can select the columns that we wanted by using this use calls. So here we can mention the column index. So here column index is nothing but this is the zeroth column, this is first column, and this is second column. We are interested in the first column and second column. That's why here we are writing use calls equal to 1 comma 2, and then we can simply print the data frame. So these are all the data points that we are having. Okay, so like I think we are having some 29 points. So if we see over here, here also we are having 29 points. So in the whole overall data set, if we look, like there are only some, so it is indexing from 0, so there are 30 points. Yeah, it is a small data set, but for demonstration purpose, I think this is good. You can even apply linear regression on big data sets as well if you think the data is linear. Okay, so let's continue and see how to do this. So first we are loading this data, and then we are observing this data frame. And then I think you guys already know this df.head will be giving us top 5 rows, and those top 5 rows corresponding years of experience and salary is shown to us. And like you have to go through the previous videos of pandas and numpy, all those things. So I have already done videos on that. So if any of these functions are not so clear, please go through that videos. It will be simpler for you. So here what we are doing, we are just taking all the input columns in X, whereas the Y output column in Y. So we are selecting the first column and we are doing 0 to 1. That is because we wanted some two-dimensional space. We wanted our inputs to be in two-dimensional. That's why we are doing this. Okay, so we are keeping all. So here on slicing like this, we'll be getting inputs in two dimensional, like 30 comma 1 like that. So if you are directly selecting 0 only, then we'll be getting only 30. But as we are doing like this, we are getting 30 comma 1. So you might be asking why we need this extra dimension. Uh, like that is needed for the sklearn library. So instead of like first taking the one column and then reshaping it, instead of doing all these things, let's directly take it like this because it will be giving us in two dimensions, right? So that's why I'm directly taking it like this. And then why like there will be always one column, and also the sklearn library will also accept in one dimension only. So that's why we can directly select that particular column. So x and y we are having. So x shape is 30 because there are 30 data points in the whole data set that we have already observed. Okay. And similarly, if we observe the x, these are our x values. What is our x? X is nothing but years of experience column. So these are all the values that are available in our data set. And similarly, if we observe y, y shape will be 30 only because it is of single dimension. And these are all the salaries of each of the data points. Before going on to any of the training part, like the main linear regression part, first what we need to do, we need to split our data. So now we are having some data set in which there are 30 points, right? So we can't use directly all these 30 points for training. Like if you use all these 30 points for training, then how will you test or how will you know how good your algorithm is? So in order to test, you need to have some points, right? So that's why we'll be splitting this particular data into two parts, that is detrain and detest. So detrain means training data set, whereas detest means testing data set. In general, we'll be following something like 80% and 20%, or we might be even following something like 75-25 like that. Like we'll be deciding what ratio to use. So in general, these are the two ratios that are most commonly used. Okay, so you can also follow any one of these. Let's see how we are doing over here. Here, if you observe, there is some function in sklearn.model selection which will do splitting for us. We can simply pass our x and y in which inputs and outputs were there, and then we need to mention the test size. Here we are mentioning 0.25, that means 25% of the points will be going into the testing data set, and remaining 75% will be going into the training data set. And here, if you observe, we are giving something called as random state. So you might be thinking, what is this random state and all? So if we have gone through the NumPy video, there you will be seeing some function called as seed. Okay. So this random state will be working similar to seed. So what it will be doing is we need to split the data, right? So while splitting the data in general, like this function will follow random splitting. So it's not like we are having 30 points, and in these first 75% of the points will be coming in detrain, and remaining 25% will be going into testing data set. It will not happen like this. Okay, so how it will happen? It will randomly choose some 75% of the points and will be keeping it in detrain, and similarly it will be randomly choosing the remaining 25%. Obviously after choosing 75 we'll be left with 25, and those will be our testing data set, right? So like this it will be splitting. But this random splitting, if we wanted to control, like next time also we wanted to split the data in the same manner, then we can use this seed. So like if without this, if we are running this particular notebook multiple times, then what will happen? This splitting will change, or the way we split training and testing data will change. Okay. So if you don't want it to change, then you can simply write it like we can fix some random state. I hope this is clear. Now, if you observe the training shape, there are 22 points in training dataset, and there are 8 points in testing dataset. So if you calculate, it will be 75% of 30, and it will be 25% of 30. Okay. So, and similarly, y train and y test will also be of same shape. Just there will be some extra dimension over here because, as I said, sklearn will be like accepting in the inputs in multiple dimensions, whereas output in single dimension. So that's why we are doing this. So in sklearn.linear model, we are directly having this linear regression. So this linear regression function, within that itself, we are having all this. hypothesis, loss function, optimizer, all these things will be done just with this one line of code. So what we need to do, we just need to give model equal to linear regression, and then we need to fit on the training data. So every time, like we'll be fitting on the training data. Please remember this. Okay. So on fitting on this training data, what will happen? The training process that we have discussed, that will happen. First, we'll initialize the hypothesis with some random parameter values or theta values, and then it will calculate the loss, and then all these will be adjusted according to the optimizer that we are having. Okay. So like that, everything will happen in this fit method itself. And after that, we'll be having model.intercept and model.coefficient. You might be thinking, what are these? So if you remember, like here, if you observe, there is only one input column, that is years of experience, right? So if you write down the equation, it will look like this. So salary equal to some m times years of experience plus c. So these two will be our parameters. So let me change the color. So these two will be our parameters, and these will be initialized randomly, and then it will be adjusted according to the data that we are having. So in general, we call this as intercept, okay? And this is our coefficient of this one, okay? So these are our intercept and coefficient. So if you have like here, if you observe, we are taking model.intercept. That means after adjusting to the data, this is our intercept. Okay. This is the optimal parameter value for C. And similarly, this is the optimal parameter value for M. So here it is 22,915, whereas optimal M value is 9,518. And then if we try to calculate the score on the training data, so we are getting some 0.97. That means you can think like 97% of the time it is giving some correct answer. But how we are getting this score? Do you guys have any idea? So let's like try to understand how we are calculating this score. So basically, let's say there is some cricketer. Okay, so there is some cricketer, for example, Rohit Sharma. So we have Rohit Sharma, and we wanted to observe how he is performing in IPL or how he is performing in some series. Then what we'll be doing? We'll be in general seeing his average score, right? So we'll be observing his average score, and then we'll be knowing that his batting or his average score is this much in this series. That means he has performed really well, or his average is lesser. That means in the series, he's not in good form. Like that, we'll analyze, right? In the same manner, for some continuous values, here, if you observe y equal to mx plus c, this y will be continuous. So in general, if we see regression problems, nothing but continuous, like we'll be trying to predict some continuous value, right? So for such continue kind of variables, it is better to compare it with average. So that is the idea that we'll be using. So for that, we'll be using some technique called as R to score. So R to score is the thing that we'll be using in order to check how good our model is. Okay. So in general, the idea of R to score is to compare with average. So let's say this is our data that we are having. For this kind of data, what will be the average of this data? Can anyone identify the average for these points? So here, what is average? So let's say this is our X and this is our Y. That means this is our years of experience and this is our salary. Okay. And let's say this is the data points that are there. Let's think of the average one. So these are all our data points, and you can think this point is the average salary of this whole data. Okay. So as I said, here our idea is to compare it with average, right? That means we'll think that for each and every input, the salary is the same. So we'll think for all the inputs, the model is giving salary as this one. That is, it is giving the same value. That is the average value. Okay. So this is what we are thinking. Let's denote pi average with pi bar. Okay. So this is the output that it is giving. Basically, if we think in general, this is not a good model, right? Which is giving y average. So, like In general, we'll compare it with average. So if you remember, we'll calculate loss like this, that is mean squared error, y minus y cap whole square. So we'll do average also. So let's for now ignore this because in denominator and numerator we'll be having average. So these will cancel out. So let's ignore this one by n. So if we take in denominator, we'll be having this y minus y bar whole square. And why are we having this in denominator? Because we are comparing our model with some average model. And here, what is our average model? Which is giving like same value for all the inputs. That means same average value for all the inputs. That is our y average. And in the numerator, we'll be having the predicted values. And what are these predicted values? This we'll be getting from the line that is given by the linear regression. So in general, if the data is linear, how how it will be giving us the line? How linear regression will be giving us the line? It will be adjusting the loss function and it will be doing that, right? So like what do you guys think? Will it be giving worse than this or it will be giving better than this? In general, if data is linear, most probably it will be giving something better than this, right? So the worst case prediction will be on this line in general. If we think the worst case prediction will be on this line. Okay. So because in general for linear data on reducing the error, the best prediction will be this one and worst prediction will be this one. Okay. Most probably in this area, our linear regression line will be there. And we need to check like how good is the line. That means this is the best line. That means for this, we need to get value near to 1. And for this, we need to get value near to 0. So let's check. So if the numerator and denominator are same, then we'll be getting 1. And when will numerator and denominator will be equal? That will be equal when like this predicted line by linear regression is on this particular y average. So in that case, it will be 1 and when it is near to best case value, so in that case what will happen, this numerator will be very less value. Okay, why is that? Because the error will be less. Okay, so because it is near to all these points are representing actual salary values, whereas on this line we are having the predicted values. So the error will be less. This is our actual y, whereas this is our predicted. Okay, so the difference between them is less. So overall value of this is very less. And similarly, if we check this value is in general very high because every time we are telling it as average value, right? So the amount of error is high obviously. So this will be some large value. So overall, if we check this overall thing, it will be going to 0. But if you guys remembered, the thing that we wanted is in reverse. For this line, we need 0, and for this line, we need 1. And how we'll be getting that? So that we can get by simply doing something like doing 1 minus this. So whenever this goes to 0, this overall R2 score value will go to 1. And whenever this goes to 1, the overall R2 score value will go to 0. So by this, we can say that whenever R2 score value is near to 0, that means the model is bad. And if the R2 score value is near to 1, that means the model is really good. Okay, that we can like observe from this auto score. So here if you observe, we are having some score over here. The score is nothing but auto score. Internally, it is implementing auto score. So according to auto score, it is 0.97. That means it is near to 1. So it is performing really well. And but on testing data, we need to see, right? Training data on that it will get trained, so obviously that value will be high. But if you observe the testing data, on testing data, it is giving 0.88. So even 0.88 is good score. If it is less than zero point 0.7 or 0.75, then like we can say that it is not that good, but greater than 0.75 or zero point 0.8, we can consider it as good. Okay. And if it is greater than zero point 0.9 or 0.95, that means really good. Okay. So by observing this, we can tell that this is good. And we can get those predictions as well by simply calling model.predict and on the input data. Here we are passing testing data. So we'll be getting predictions for our testing data And if we observe those testing data in the form of data frame, so here we are just doing some kind of reshaping kind of thing. That's it. So no need to think too much about it. Here first, as we are having two dimension in X, we are like reducing one dimension, and then we are showing the predictions. Okay, so that's it. And then if we plot the things, we have discussed how to plot and all using matplotlib. So here we are plotting based on training data. So here X-train and Y-train. So this will be giving us the points, actual data points, all these red points, whereas X-train and model.predict. So in general, as the model is linear model, it will be giving us some straight line. Okay. And if you observe, this line is near to almost all these points, right? So that means the model is doing good in this. And why is it doing good? Because it is training data. Obviously, for this, it will do good. So let's see on the testing data, this graph. So if you observe on testing data, our graph is looking like this. Yeah. So we can say it is good only, not that bad, right? So if these points are little more far, then our art score might be even bad. But to some extent, this is good only. Okay. So this is about this particular